Moose tracks.
I-
Okay, good choice.
I like ice cream social, and if I can, I get a watermelon sorbet there.
Oh, okay. All right. I haven't had that there. Ooh, I love like mint chocolate chip was always my favorite when I was a kid. And it's still one of my favorites, but I'm kind of picky about one thing. Like, okay, Breyers, I love the mint in the mint chocolate chip. It's like it's the best mint. But they're really big chocolate chips, and when chocolate's that cold, like it gets waxy and it sticks in your teeth. And I don't like that as much. So I like if you go to Baskin Robbins, their mint chocolate chip is like little flecks of chocolate and it's not so big chunks. Don't like their mint as much, but I like their chips. So as I've gotten older, I've gotten pickier about my mint chocolate chip. So what's Udu? You can't describe it? What's in it? It's cookie dough? Oh, wow. That sounds good. There's a place in Marietta I go to sometimes. It's a bubble tea place, but they have edible cookie dough dessert. It's just cookie dough. Like it's a little tub with like edible, so I guess it doesn't have raw egg in it. But it's like cold and you just eat it off a spoon and it's really good. I love it. Oh, was it good? Yeah. Are you serious? I was afraid it was gonna tank. I was like, I don't know if it's gonna be any good, but you liked it? It was good?
The end, Steve meets Alex.
Okay, cool. And isn't Jack Black in it?
Yeah.
Yeah, okay. He makes almost anything worth seeing. He's funny. Have you seen Nacho Libre? It's a movie where he plays a Mexican wrestler. It's hilarious. It's really hilarious. Like that's his wrestling name is Nacho Libre. It's funny. It's stupid.
So I saw the Minecraft movie at my first drive-in movie. I ate a whole thing of cotton candy.
Where'd you
all
go
by
to a
myself.
drive-in?
There's one in Alabama.
Okay. That's so cool.
Me and Papa also had shared. Oh, me and Papa also ate a whole thing of buttered popcorn.
Oh, yum.
When the garbage man was fighting the chicken,
Mhm.
the zombie jumped out of the roof and landed on the chicken, and Steve yelled chicken jockey. And in Minecraft, a zombie chicken is called chicken jockey.
Oh no, so it turned into a zombie chicken? Or did it just stay? No, the chicken didn't turn into a zombie chicken?
The zombie just broke on.
Oh, the zombie rode on. Okay, that's funny. Okay. That's funny.
Garbage man kept saying like, he said, "Buenos dias, that means see you later."
Yeah.
That means good morning.
Yeah. That's funny.
He said something that means goodbye, and somebody was like, "No, it doesn't."
Yeah, yeah. That's funny.
And there was also a jetpack at the beginning and at the end of the movie.
Oh, wow. I've only ever seen one movie at a drive-in, and this is funny. Okay, so I was visiting Jason, when he was in college, he did this thing called co-oping where like he did a semester where he like interned at a company that he might work for when he graduates, and then he would go back and do a semester of school, and every other semester he alternated. And so he co-opted in Raleigh-Durham. And we were out driving around one day out in the country and we found a drive-in and we saw Toy Story at a drive-in. It was really cool. It was the only time it's Toy Story. It was the only time I don't think it was the original run because I think original run had been a little earlier, but still fun though.
So there was a mention of Techno Blade in the Minecraft movie. Like there was a pig walking with a crowd, and they said, "Is that pig a king?" He said, "No, he's a legend."
No.
It was the loudest movie I've ever been to.
Loud?
Yeah. So it was just sound, and there was nothing on the screen. So people were just talking.
Oh,
and somebody
man.
shouted, "When I say chicken, you say jockey."
Oh no. So then the crowd got into it, started yelling. Where did you see it?
I forgot what
Near local theater?
drove and we made us play.
Your who drove?
My older brother drove.
Oh, Liam drove. All right.
He didn't do the best job.
Hey, it's all right. You gotta learn.
When it's like morning in the whole world
Mm-hmm.
and garbage
My mom
man broke the orb.
Mhm.
Steve appeared and he was like, where's the orb? Somebody's garbage man destroyed it. Yeah, and he was like, nuh-uh.
Oh my gosh. So apparently these girls saw the Minecraft movie over their break. So did you see it?
Oh, no, but I'm gonna see it Thursday with my
Okay, there you go. And are you seeing it? You got any interest in it? Yeah, it's like
Lucy, do you know who Technoblade was?
Yeah. I don't
So Technoblade, do you know who Technoblade?
I don't. I've never played Minecraft. I've only ever watched other people play.
He was a famous Minecraft YouTuber who lost his battle to cancer.
Okay. So they referenced him. That's nice. That's very nice.
Wait, how do we reference him? I know a secret.
She said they did. Yeah.
Enderman is a YouTuber,
Mm-hmm.
and Endermen are like builders that
Yeah.
go into the Ender portal and ate the fruit, and then they turned into Endermen. That
Okay.
actually sounds really cool.
Yeah. That does sound cool.
It's like a big like playlist
Mm.
about like Minecraft games.
Well, I didn't go to the movies over break, but I did get to go to the theater on Sunday night, and it was a kind of a last minute thing. I have a friend at the show, that the musical that was in the Fox for the Broadway series this last week. I really wanted to see, but I didn't think I was going to be able to see it because Drew had regionals, and I didn't know when he was going to compete. And we never know until like 2 weeks out exactly when he's going to compete. So I figured, I was like, sure enough, I'll buy tickets, and that'll be the time he's competing, and I won't be able to go. So I didn't buy tickets, but then my friend ended up not being able to go kind of last minute. So she's like, does anybody want tickets? And I was like, so Jason and I went down to the Fox and saw a show on Sunday, Parade, which I really wanted to see because it takes place in Atlanta. So it's a big historical event that takes place in Atlanta. So it's really kind of cool to see it. Who's that?
Raina, I don't know if I'm gonna say her last name correct. Raina Talagemeyer.
Okay.
She wrote Smile, Sisters, and Guts.
All right. And you like these,
I'm
huh?
gonna go meet her about her new book.
Was it like a book signing or something, or?
Yeah, she's gonna sign them.
Oh.
One of my
Where is that?
Decatur. He said something that was in a commercial. The whole crowd would clap.
Ah! Well, that's funny.
Last
Oh, yeah.
time, Sebastian, who is Mr. Bucket,
Mm-hmm.
doesn't know like any of his lines.
Uh-oh, that's not good when you're going to final dress.
Wait, what's
Yeah, yeah.
Sebastian? What, does Sebastian have a blonde haircut? Does he have black hair?
No, that is very short.
Different Sebastian, I
He
guess.
talks in like a very high pitched voice, like he's talking to a baby.
Well, that makes it hard to understand too.
No,
Yeah.
Sebastian.
Oh, yeah?
When he's saying a long line, he will like say a bunch and he'll pause. He'll just go. "La, la, 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 la."
Oh, that's
I
fun.
also said you have to learn all your lines, and then I was like, I learned all of mine the first day, and then one of his friends was like, no, you didn't.
Yeah. Well, it was funny when I was teaching at Cottage School, I taught music theater for like an after school extracurricular, and we were doing this musical of The Wind in the Willows, and it was hilarious because I had this one girl who like she struggled a lot in class, like she had a lot of trouble learning stuff. But somehow she went home and memorized like the entire script in one night, which was like it was like a weird miracle. But the problem was that she memorized it, but she didn't memorize it with any understanding of what the lines were, just the words. So the inflection for everything was wrong. Like there was one line that she had to say, any port in a storm, which basically means like, I'll take any help you offer me, right? But because it started with any, she thought it was a question. So she kept saying, any port in a storm? I'm like, no, it's not a question. It's any port in a storm. She said it like a question for about a month and a half until we were ready to go on stage. And then she still said it like a question. That's hilarious. She had memorized it one night. I was like, oh. For sure do it.
I've always wanted.
I've got a former student who's not with us this year or last year. even though I had her before that, because she's doing the Dexter Mosley thing and she does theater at Cambridge High School. That's her extracurricular thing that she's doing at the public school, but she still homeschools.
Caitlin.
She's great.
Caitlin in this
Mhm.
class.
Yeah.
Her and my older brother used to be best friends, so we went to her performing the Newsies.
Oh, yeah.
She was
Mhm.
one of the New York Newsies.
Yeah.
It was a really good play.
Yeah. Well, if y'all get me your Willy Wonka information, I'll check my schedule. I always try to go to student stuff. I just went to that former student show and I was trying to get to one of Ridley's dance things and I could not swing it, but I always try. I always like to know when it is. All right. Oh, okay. You can always let me know. I can always try. I can always check. Well, then maybe not. All right. Are you ready to get your notes out so we can do our best here with some of this? Some of this stuff is going to be like extra for you guys and just sort of additional information. We're just touching on, nuclear we touched on. Now we're touching on organic chemistry, which is chemistry of living things, carbon-based compounds. And we're hitting on this right at the end of the year because it's a perfect bridge into biology next year. Because now you'll have an understanding or a basic understanding of the molecular structure of what we're talking about next year, which is helpful. All right, so today we are talking about carbon compounds and how to name them. All right, so if you go to college and you're getting a STEM degree of any kind, especially if your STEM degree involves chemistry or biology, you're going to be required to take organic chemistry. And a lot of people will talk about how this is like the hardest chemistry. And in some ways it is, not so much conceptually, but that there's a lot of stuff that you just kind of have to memorize. Like it's a lot. And it's basically about how you name these compounds, and you name the compounds based on their structure. And, we talked about naming compounds. Remember, like we did eights and ites, like carbonates and sulfites and sulfates. Remember we did that way back at the beginning? That was easy compared to some of this. Some of this is like, I thought it was the hardest class I did when I was in college. And it's funny because I remember it as being a class that I struggled through so hard that I thought, when I look back on it, I thought I got like a low C, like I barely got out of it, with my dignity intact. But when I went back and looked, I got like a B in that class. But it felt like I was slowly dying every day. She would have, yep. If she hasn't, she will soon. And it can be, the labs were the most fun labs, but the class was really challenging. Some people don't find it challenging. I find it very challenging.
My dad has the.
What's his degree?
I don't know.
Do you know? What is he?
He just told me. I asked him,
Yeah.
you know what? Something about chemistry. He said, "No, I only did organic chemistry."
Yeah.
So
I thought I had to do like 1 and 2.
He said
Organic
it
1,
was
organic 2.
really
It is really hard. But fortunately, at your level, you don't have to do, you're not going to be responsible for the hard stuff. I want you to kind of know about it, but I'm not going to make you responsible for it. All right, so let's talk about compounds of carbon, and that's what we mean by organic. Now, when you see the word organic in the store, like you see organic tomatoes, what does that mean?
It's like fresh tomatoes that are like no chemicals.
Yeah, so
Pure, fresh.
what they mean, like when you
It's
see
organic water, like distilled water.
Yeah, so when you see organic in the store, like organic tomatoes, organic apples, what they're trying to say is that the fertilizer and pesticides that they used were not synthesized in a lab. Like they used manure instead of chemical fertilizer. Everything's chemicals, right? The tomatoes made of chemicals, we know that, right? But if you have an organic tomato, that's what they're trying to say. That they didn't, and also that they didn't, a lot of times it sort of doesn't always, but sometimes it implies it's not genetically modified. But if we're being technical, pretty much everything we eat has been genetically modified. You'll hear about GMOs, genetically modified organisms, like, oh, GMOs are bad for you. But we've been genetically modifying our foods since we started farming, since the earliest days when humans started growing things. Do you know what corn, an ear of corn looks like? Picture an ear of corn, right? Do you know what corn looks like in the wild, like wild corn? It looks like a blade of grass with a couple of little random kernels stuck on the top. It doesn't look anything like the corn you eat. And that's because we've modified it, selective breeding.
Did you get a pet fish?
I did. Yes, this is Linus, by the way, for everybody who missed him earlier. Yeah, you can have a bean. I-
beta fish?
He's a beta. I haven't had one for a while. My last one died and I wanted to replace him, so I replaced him. And
I don't see him.
he's back here in the screen. Look from the top. And I always name my fish after scientists. So he's named after Linus Pauling, who is a very cool guy. All right, so so organic, when we're talking about chemistry and biology, does not mean the same thing as organic when you see it in a store. So does anybody know what an allotrope is? Does anybody know what this word means? All right, so an allotrope is it's a different presentation of the same element. So for each of two or more different physical forms in which an element can exist. So for example, graphite, charcoal, and diamond are all carbon. They're all pure carbon. But graphite's what's in your pencil, right? When you write, they call it pencil lead. It's not lead, it's graphite. And charcoal is carbon, and a diamond is carbon. How can this diamond here on my ring be the same as what you're writing with in your pencil?
Because it contains carbon,
They both contain carbon, right? But they're so different. Why do they look so different?
different elements combined with.
It's not different elements because we're talking pure carbon. So what it is it has to do with how those molecules or compounds, basically functional units, no, formula units, sorry, are arranged within each other, and that is often due to how it is formed. Diamonds, you guys know or probably know, are formed under like intense heat and pressure, right? Graphite, far less heat and pressure. So that's how we get different forms of carbon. So the properties of carbon allotropes depend upon the arrangement of the atoms and how they're bonded together. So allotropy is the property of some chemical elements to exist in two or more different forms or allotropes that are found in nature. And there are several different allotropes of carbon. So we named graphite, charcoal, and diamond. Anybody think of anything else?
Miss Danny, I'm having trouble.
Yeah,
finding-
I'll help you. What'd you say? You know, lava? Okay, good name. You gotta push them 100 degrees because they have like a, there you go.
You-
Stones and stuff like that.
Stones and stuff like that. Yeah, okay. So these are all carbon atoms arranged in different ways. So they're arranged as different allotropes of carbon. So here's what they are. A is a diamond. That's how carbon is arranged in a diamond. B is graphite. That's what you
Oh.
write with. Now, do you see how when you write, you see how they're like almost like little flat, they're little
Yeah.
planes, right? Little flat planes. So when you write, you see how that would like kind of shear off the end of your graphite in your pencil and stick to a page? It makes sense, right? C is Lonsdaleite, which is a different organization. D we call C60 or Buckminster Fullerene or Buckyball. Isn't that fun? Buckyball. Sounds like something you get at a cool gas station.
It sounds like what we're doing for lab today.
Yeah, that's bouncy ball. E is what we call C540 or carbon 540. F is C70, carbon 70. This is amorphous carbon.
No, that has a lot of carbon molecules.
Yeah, which is kind of like coal. You can think of it like coal. And then this one is a single-walled carbon nanotube or a Bucky tube. So we have a Bucky ball and a Bucky tube. Those are fun, right? So those are all just different arrangements of carbon atoms. So now let's talk. What is a hydrocarbon? It's the simplest organic compound, and it's composed of only two elements. And what elements do you think they are? What do you think is in a hydrocarbon? What do you think, Eunice? Hydrogen and carbon. These are the two elements that when they're combined together, you end up with a hydrocarbon. Hydrocarbons are extremely prevalent. They are everywhere. You have billions and billions of them surrounding you and in you. And here's some examples. Methane, ethane, and then ethene. Oh, you see what I mean about naming compounds and how it gets difficult. See how these only contain hydrogen and carbon. Do you see any other atoms in there?
No.
Just hydrogen and carbon, but look at how they're arranged. This one gives you methane, this one gives you ethane, this one gives you ethene, And then this is a slightly different organization of ethene. But it's all the same. So how they're organized is how you name them. See how similar the names are? So you see what I mean about how organic chemistry can be really challenging because there's so much like to memorize, all these naming standards. So hydrocarbons themselves are separated into two types. We have aliphatic hydrocarbons, which are hydrocarbons based on chains of carbon atoms. And then those have three types, and they would be alkanes, alkenes, and alkynes. Okay, remember but what did I just say about naming? That naming.
Alkenes,
Yeah,
alkynes.
so alkanes are aliphatic hydrocarbons with only one single covalent bond. And alkenes, are aliphatic hydrocarbons that contain at least one carbon double bond. And then alkynes are aliphatic hydrocarbons that contain a carbon triple bond. And occasionally we'll find an aliphatic hydrocarbon with a ring of carbon atoms, and they're in a ring. You can think of them in a ring, and they're called cycloalkanes because it's like they cycle around. Yes, Annabelle.
So,
Did you have a question? Your hand was up. What you need? You want me to come back to you? Y'all are passing notes, but you had your hand up. What's your hand? What do you need? Do you have a question?
so is this our final lab?
No. We got labs after this.
But
We
next
still have to do a DNA RNA game.
but next week is
Next week is break again. This is the weird
Easter
week.
break.
Yep. This is the weird week where we have usually spring break and Holy Week align. Either they're the same week or one follows the other, but this time there was a gap.
Next week is Easter.
This Sunday is Palm Sunday, so next week is Holy Week. So it's Palm Sunday, Monday, Tuesday, Wednesday, Monday, Thursday, Good Friday, Holy Saturday, Easter. And we're off that week because I'm at church Thursday, Friday, Saturday, and Sunday. Because I have a lot of singing to do. and I live, well, Sunday, and then Thursday, Friday, Saturday, Sunday. There you go. All right, so these are all aliphatic hydrocarbons, and they're hydrocarbons based on a chain of carbon atoms, and you have your three types, alkanes, alkenes, and alkynes. All right, so what's the second type of hydrocarbon? Aromatic hydrocarbons. So aliphatic, aromatic, of course they have to rhyme and start with A because that makes it so easy, right? Aromatics. And these are things like benzene. These are flat ring systems that contain continuously overlapping p orbitals. Remember our sp, remember our orbitals? These overlap, and electrons in benzene ring have a special energetic property that gives a benzene ring and chemical properties that are markedly different from alkanes. So you have basically it's a ring, and some of, like 6 or 5 carbons, and they're in this ring together rather than in a chain. So these are aromatics. And originally, why do we call them aromatic? You think aromatic means it smells, right? It has an aroma. So originally the term aromatic was used to describe this class of compounds because they were particularly fragrant. However, in modern chemistry, the term now denotes the presence of a very stable ring that imparts different and unique properties to a molecule. So aromatics are those in a ring, all right? So aromatic, aliphatic, and there are 3 types of aliphatics, right? So here it is. We have a cyclic or open chain or aliphatic and a cyclic or closed chain. So let's see. This is where it gets a little tricky. There are here's our alkanes, alkenes, and there's going to be something here. So let's see if by process of elimination we can figure something out. It says acyclic or open chain or aliphatic. So no, we're dealing with aliphatic, not aromatic, right? If this one is unsaturated, what do you think the other category would be?
Alkynes.
Well, hang on. If it's unsaturated, what do you think the other one might be? Just by process of elimination, if you had to guess.
Alkynes.
That's a good guess. If it's not unsaturated, what would it be? What do you think?
Saturated.
Saturated. There you go. Okay. So basically you have saturated, unsaturated. And your saturated is where your alkanes go. All right. And then we take those alkenes and what?
Alcohol.
Alkynes, and those go into saturated category.
Saturated.
Ah. So we have aliphatic, and we said we have 3 types of aliphatic: alkanes, alkenes, and alkynes. And the alkanes are considered saturated, and the alkynes are considered unsaturated. Now let's look over here. We have cyclic or closed chain. We have alicyclic, and then what do you think? Non-alicyclic? That's a good guess. This one is going to be aromatic. That's where you see your aromatics, right? Remember we said we call those aromatics. So the ones that are alicyclic, we can say they're saturated or unsaturated, but let's look here. Aromatic, if it's non-benzenoid, then what do you? Benzenoid, that's exactly right. So basically, this is kind of what you call a dichotomous tool. It's like you branch off this way, and you, like, for example, we could do it like this. If we're trying to figure out who in the there's 4 of you. Okay, all right. So you could say question 1 on the dichotomous tool: boy or girl? Girl. So we're gonna step over in this category. We know it's not going to be Eunice. Okay. Then let's see. Ponytail or no ponytail? Let's say it's ponytail. All right. So now we're walking away from Lucy, right? All right. And then say it says glasses or no glasses. If it says glasses, then we know the answer is going to be Emerson, right? So that's how a dichotomous tool works. And that's kind of how this works. You can use one like that to name. Dichotomy means opposites. So it's either glasses or no glasses, ponytail or no ponytail, boy or girl, like in this case, right? All right. So let's have a look at this. Functional groups. Oh my goodness. So organic compounds are classified by their, functional group. So in organic chemistry, a functional group is a specific group of atoms or bonds within a compound that is responsible for the characteristic chemical reactions of that compound. The same functional group will behave in a similar fashion, undergoing similar reactions, regardless of what compound it's a part of. So functional groups play an important part in organic nomenclature. Nomenclature is naming, or the process of naming. Combining the names of the functional groups with the names of the parent alkanes provides a way to distinguish compounds. So you have an alkane, and then you add something to it. So at the top, you have alkane, alkene, alkyne. There's an alcohol, an ether, an epoxide, and a haloalkane. Well, that's fun, right? And then underneath, you have, look at these: amine, nitrile, imine, isocyanate, azo compound, thionyl, arene. This is where organic chemistry gets really complicated, because what you need to know is how to go about combining these to properly name a compound. So, for example, under the ester, it says naming YLOATE. Example, ethyl ethanate. Oh, that's fun. That's if you're using the ether above. So if you have ether with an ester, it's now ethyl ethanate. So it's kind of like you take these basic molecules, your alkanes, your alkenes, your alkynes, and then you pop different hats on them and you name them based on the hat. Red hat, blue hat, orange hat. He's a chef. That one has a chef's hat. That one has a nurse's hat. That must be a nurse, right? That's how you identify. That was a police hat, so it must be a police officer. That's how you identify them, right? Okay. So functional groups are often used to functionalize a compound, affording it different physical and chemical properties than it would have had in its original form. Functional groups will undergo the same type of reactions regardless of the compound with which they are a part. However, the presence of certain functional groups within close proximity can limit reactivity. Functional groups can be used to distinguish similar compounds for each other. So this right here, this type of idea that you can take a functional group and it's going to behave similarly no matter what base molecule you're putting it on. It's kind of like saying, if I put on a chef's hat, I become a chef. And if I take it off and I put the chef's hat on Eunice, now he's a chef. Okay. He may be a different chef, but he's still a chef. This is how we get pharmaceuticals that work really well. This is one way that we do that. We get pharmaceuticals that work very well. And one thing you can think of, there are these things called isomers, where it's like basically you have a molecule and it looks like this. Everybody see how this looks? Okay, let's say it looks like that. All right, this is your molecule. Yeah, let's just pretend this is your structure. This is molecule A, that is its isomer. Best example of an isomer or something very similar to an isomer in recent use was back when COVID was like here, and we were all trying to avoid it. Nobody loved it. One of the initial debates that people were having was about a drug called ivermectin, which is used in veterinary medicine. But some people were swearing up and down that ivermectin could be used to combat a COVID infection. And other people are going, you can't use that. That's a veterinary drug. You can't use it on humans. It's for like horses and cows and things. Well, what they came out with, what they gave everybody was Paxlovid. Anybody take Paxlovid? I gotta take it. What? Paxlovid is basically similarly functions like an isomer. If this is ivermectin, this is Paxlovid. So the ivermectin people, in a way, were not wrong, but they changed it just slightly enough to market it to humans, but chemically it was nearly identical to the ivermectin we started with. So see, they can be very similar. All right, names and structures of organic compounds. Here comes the fun. Woohoo! Names and structures, naming. How do we name these things? The names of what are the basis for the names of hydrocarbons? What do we say? Which thing?
Hydrocarbon.
Yeah. So it's our alkanes. We're going to start with our alkanes. And these are the basis of the names for most hydrocarbons. That's because they're very common. So you identify the root. Then you identify the longest continuous chain. Then you find the root name for the number of carbons in the chain. And then you identify the suffix. So for example, the longest chain has 6 carbon atoms. Do you see the longest chain?
Yes.
It goes this way, right? 1, 2, 3, 4, 5, 6. Does everybody see it?
Yeah.
So you go, okay, 6 atoms. The root name is hex. Why? Hex is 6, right? Penta is 5, tri is 3, quad is 4, hex is 6. A hexagon has how many sides? Well, you see 6? How many sides does a hexagon have?
6.
6. Hex is one of those roots and prefixes, right? So now we have hex. So the compound is an alkane. The suffix is ane. That's how we do it. And it's crazy difficult. And this is why. Hello, here are some examples for you. Welcome to organic chemistry. Yeah, and if you do it in college, you're going to be expected to know all of that. Not just be
More.
familiar, know it exists, like know it. It's a lot. There you go. So you can see all these. So over here, like example, it says, here are your roots. Here are your functional groups. So for example, if you take a look at this one, name is pentane. Where's a good one to do? Okay. Pentylamine. Pentyl, it's an amine. It's pent, amine, pentylamine. See, gets to be a lot of fun. All right, modeling. How do we model these things? Oh my gracious, you're talking about not little, this isn't NaCl, this isn't H2O. These are big molecules. So there are different ways to model organic compounds. Each has its advantages. So you can do a structural formula, and that's these right here. So that's methane at the top. Does anybody know what methane is? These are all gases. Okay, and methane is flammable. Like you may have seen it on the, like, used it in different ways, but it's anyway, it's
Do you have to know all these?
no, you don't have to.
Oh.
But you can do it structurally. Now look at that. Methane has how many hydrogens
4.
and how many carbons?
1.
And it's a single bond between each, right? See how there's one line, but look down here at ethane or ethylene. How many carbons? 2.
Yeah.
And how are they bonded? Singular or double bond? Right here.
Singular.
Right there. Double. See the double bond?
Oh.
2 lines, double bond. with a single bond of 4 hydrogens. You can also do it ball and stick, or what they call space filling model. Yes, ma'am.
Never mind.
Never mind? Okay. So what kinds of organic reactions are there? Oh, there are so many. So polymers, this is what we're dealing with in lab today. So be sure you're tuned in right now so you have an idea of what you're dealing with today. A polymer is a large, anybody know? What are you thinking about?
Molecule.
A large molecule? So yeah, it's going to be a very large molecule made up of chains or rings of linked repeating subunits, which are called monomers. Okay, polymer, monomer. What is the same between the word polymer and monomer?
Mer.
Yeah, omer, right? Poly means what? Many. Mono means what? One. So polymers have many units in their chain. Each of those units is called a monomer. So singularly, one is a monomer. You put them together, they make a polymer. Polymers usually have, what do we think? What and what? High, what and what? They have high melting and boiling points. Because molecules consist of many monomers, polymers tend to have a high molecular mass. These are big molecules. You see that thing at the top?
Yeah.
That is one molecule. These are big, big molecules. They are chains. And we're going to find out when we start talking about them. But proteins are so big that they fold up like origami in order to function. They're so long that they fold right up, almost like a transformer turning back into a car and squishing itself down. So like I said, the word polymer comes from the prefix poly, which means what, everybody? Poly means?
Big.
Many. Poly means many, right? And the suffix mer. Okay, what do we think mer means? Well, mono means one. Muppet. What do we think? So mer means parts. So a monomer means literally what? One part. And a polymer means many parts. Yes, good. So the word was coined by a Swedish chemist named Jan Jakob I always say his name wrong, Berzelius. Well, it would be Jan because he's Swedish. So he's not John, he's Jan Jakob. In 1833, along with a slightly different meaning from the modern definition, the modern understanding of polymers as macromolecules was proposed by German organic chemist Hermann Staudinger and in 1920. Okay, macromolecule. There's a word for you too. What's the root word in macromolecule? What's the root?
Macro?
That's the prefix. So the prefix is macro. What's the root?
Molecule.
Molecule. What does macro mean?
Macro means big, a lot.
Big, because what's the opposite of macro? Micro. So micro would mean it's tiny, a micromolecule or microscope. I look, I scope, I see small, right? Yeah, two
Is there a
small.
macroscope or a telescope?
A telescope, you see far away, coming from far away. Television, you see something coming from far away. Telegraph, it writes a message from far away, right? So this is why we learn these roots and prefixes and suffixes, because they help. So a macromolecule would be what? A big molecule, right? All right, yes, ma'am.
Oh, I thought you were gonna.
Oh. Okay, so let's talk about this. We have something called a substitution. So just know these exist. You're not going to be tested on these like heavily. So an atom or a group of atoms is replaced in a substitution. So in this case, we're going to take OH, we're going to add HCl, and then we get this little dealio here plus this H2O. So you can add or replace something in what's called a substitution in an organic molecule. You can also have what's called an addition. An atom of group of atoms is added to replace a double or a triple bond. So in this case, you're adding something here that is going to replace a double or triple bond.
It's an and.
And where?
Is added to
Replace and. Oh yeah, it should say A. Very good, you caught one. You know, write it down before you leave and stick it over there. All right, and then you can also have what's called elimination. And in elimination, you have a pair of atoms or a group of atoms that are removed from a molecule, usually through the action of acids, bases, or metals, and in some cases by heating to a high temperature. And that would look like this. So these are just different things you can do with them. Now we have this condensation. All right, now you have to think completely differently here. When we think about condensation, we think of it as a phase or a state change, right? It's when something goes from what phase to what phase.
Hot face to cold.
Well, that usually causes it, but it goes as what?
Gas to liquid.
Gas to liquid, right? Okay. But in organic chemistry, condensation means something different. It means a molecule, usually water, is formed by combining atoms from adjacent carbon atoms. So basically, it's when you add a water to something in organic chemistry, when you add a water molecule to another molecule, it's called condensation. And you can think about it like if you have a cold glass on the table, you see it kind of looks like that water is being added to the outside of the glass. It's not really, right? We know it's just condensing. It was there already, but we call that condensation in organic chemistry. So it's very different. All right, now I'm giving you a heads up on your homework. Your homework, you're going to be looking into who invented Kevlar, in what year, what was this chemist's initial goal, for what company did this chemist work, and did this chemist win any awards for this invention? And have you been alive at the same time as this chemist? And are you still, meaning is this chemist still alive? And what are some applications of Kevlar? Does anybody know what Kevlar is? So Kevlar is a material that's used in, for example, bulletproof vests. And this is part of your homework, but I'm giving you a heads up now because this is really cool. This is all about Kevlar, who invented it, and how it was invented.
What I love about my work is that I have the opportunity to be creative every day. I love the excitement. There's something about me, it's an inherent part of me that wants the excitement of invention and creativity. My schooling was somewhat different from what it is today because we had 2 classes in one room. This was in a public school. Frequently, you'd finish your work and you would hear where someone was having trouble in the next class. You would put up your hand and you would give the answer, especially in math. And this went over like a lead balloon. But what you really did was you learned 2 grades at one time. I loved learning and loved learning new things. I found it very exciting. So this probably made me what I am today and what I was for many years. When I entered the workforce in 1946, not many women were being hired, but the few that were, they were hired because there were so few men available. They were at war or just coming back from war. So women were being made offers, but that didn't mean, that the problem was completely solved because women had a very difficult time after they got jobs. And many women did not stay very long, but I was stubborn and I decided that I was gonna stick it out and see what happened. And things improved eventually, but I didn't stay just because I was stubborn. I stayed because the work was what I wanted to do. It was 1965 and I was assigned to look for this super strong, super stiff, but lightweight fiber. In the course of that work, I made a discovery. The results came back. It was very strong and very stiff. Unlike anything we had made before, I hesitated about telling anyone because it was unusual and I didn't want to be foolish. And so I sent it down a few more times and it always came back more or less the same numbers. And so I then told my supervisor and we in turn told the laboratory director and everybody became very excited. So that was the beginning of Kevlar.
So she
I was
invented it.
elated to have made this discovery because most people work a lifetime and they never do anything like this, something that saves human lives. I think the role of science is to improve human life in general and improve the world as well. When I reflect back upon my career, I am inspired by the fact that I was able to do something that was of benefit to mankind.
So you're gonna end up having to tell me who she is.
It's Stephanie Koala.
What-
Stephanie Kowalik. Yep. So she invented Kevlar. Oh, you have to look it up, see if she's still alive. And I have one more for you. So yeah, it's in there. So this is something else. So dimethyl mercury, all right, is an organic compound that poses a serious environmental threat to all living things. So this is what the seniors are going to do. They're going to research how this compound affects living things and include information on whether dimethyl mercury poses a threat to your local environment. Okay, what do you know about mercury in humans? Do you know?
It's fine. Liquidy metals.
It's a metal that at room temperature is in liquid form. Yeah.
But you cannot touch it because it's
Toxic,
toxic.
right? Okay. Now,
It can be used to identify temperature.
it can be, yes, because it can be used to be put in thermometers all the time. Now we use alcohol thermometers much more often. Now, here's the thing about mercury. There was a time period where humans were consistently exposed to dimethyl mercury, and here's how. This is crazy.
Today,
Sorry.
$8 or more, just $1 down. The Atlantic Friday, April 11th.
Scared me.
Sorry. Always for commercial.
Personally, I go to Sparkle. It cleans everyday messes and it won't clean out your wallet. And too.
Okay.
This episode is sponsored by Wix. Go to wix.com/go/simple history to create
Have
a
you?
website today.
Right. So
Dangerous jobs in history. Hat maker. When you think
think
of
you
a
guys
dangerous
saw this
job
one,
in
didn't
history,
you?
you might think of the occupation of a soldier
So
or
she
someone who
watches for
dealt
just
with
a few minutes
disease
till
like a
class
plague
breaks up.
doctor. But you would not think that hat making would be so dangerous. In the 1500s, the milliner became a term to describe a trader that specialized in importing women's accessories from Milan. As hats began to become a
So,
popular status
to watch
symbol
to be
for men
fair-
around the 14th century,
does anybody remember how they got exposed to dimethyl mercury? You remember? Yeah, they were using it in the hats, but where'd it come from? Do you remember?
The hat.
So one of the things used to help tan pelts and leather and things of that sort was urine. It was actually the ammonia in the urine that they wanted, but they were using urine. So if you were really poor, you could sell your urine to a milliner or a hat maker, and that would be some money. Yeah, they would pay you for your pee. Yep.
Yeah.
You could sell that, and that would be a way that you could get some money to go eat, right? But also at the time, there were a lot of diseases that were really common, and they were treating some of them with mercury, which is toxic and not good to treat with. But that would mean that some of the mercury in your body would get converted into dimethyl mercury, and then you would pee that out. And then that mercury was in the urine that the milliners were using to help prepare the materials for the hats. And then they were getting exposed to it a lot. Well, we won't have time to finish the whole video, but I wanted to remind you of it, and it's in your resources. Yeah. So this is where you get dimethyl mercury. So it is a thing for sure. And it caused a lot of people to go wackadoodle, right? Total wackadoodle. So we won't have time to finish it because it's time for this other class. But it's there. So you know how to get a hold of it and watch it again if you want to, even though it's absolutely crazy idea. Because that's where the term Mad Hatter comes from. Because the guys that made the hats were so exposed to mercury that they had the neurological effects of it and they went mad or crazy.
We need a lot.